All right. Good afternoon, everyone. Can everyone hear me? Okay. Don't forget, you have an exam that's due tomorrow before midnight. Don't forget about that. I know I keep reminding you, but I'm going to keep reminding you because it's there. And also, don't forget to read the exam instructions before you take the exams. Because the last thing I told you was that the exam instructions change. So I haven't changed them since. I'm just letting you know that they have changed since the last time I told you. That's the only time. So make sure you read those instructions before you start the exam. Any questions on what I just said? No? Okay. Just trying to make sure. Oh, that's right. Sweet. D20. Okay, sweet. Ah, okay. So the last thing we did. Oh, I forgot to look at that example. I knew I forgot something. Was we may do only one or two sections today. I'm not so sure, honestly. I know we're going to finish chapter 6 for sure, but I don't know if we're going to start chapter 7. Maybe, maybe not. We'll see. Sure, if it was up to you guys, it'd be like, oh, no class today. But it's not that simple. Okay. One can only hope. True, true. Maybe one day we'll see. Okay, what was the last section I did? 6-3. So this is the last section I did. Permutation combinations. Okay, so we're gonna do section 6.5 today. Um, Now with section 6.5, and again, I'm gonna state this again. Well, actually, no, it's the first time I'm stating it today. I should say that. For section 6.5, you have to remember that from section 6.3, permutations are only used when what? When to use a permutation and when is it best to use a combination? Can anyone explain just really quickly? When do you use a permutation? When do you use a combination? In general sense. Right. When order doesn't matter, correct? Combination. Depending on if order matters. Exactly. Perfect. If order matters, you use a permutation. If order does not matter, you use a combination. That's probably the most important thing about a combination and a permutation. Now, keep in mind that in some calculators, you can use permutations and combinations. You can type in your calculator so you don't have to worry about doing that long um, arithmetic. But if I don't ask you to simplify, chances are I want it in terms of the permutation or combination or whatever way form it is in of terms of defining the answer and whatever form of counting. Okay. So make sure if you plan on using a calculator, you know how to use your calculator for permutation combinations. Because if I give you an exam that asks for that and I just want the answer, make sure you know how to use your calculator right away. Because if you don't, then you're not. It's going to take some time. So make sure you can find them within your calculators. And again, the calculators are allowed in this class of scientific calculators. Graphing calculators, not so much. I would prefer you not to use a graphing calculator. I would prefer you to use a graphing calculator. That made no sense. I would prefer for you, I want you to not use a graphing calculator. I want you to use a scientific calculator, okay? Now, let's start with section 6.5. Section 6.5. Now for this section, I'm actually going to do, not all of them, but I'm going to do a couple of problems that the book explains, because I want to give kind of like a deeper understanding of those problems, those examples. And you'll see what I mean in a sec. Okay. What day is today? Today is the 28th. Okay. Sweet. So let's start off with this. Let's start off with an example. Example, not example. Okay. How many ways can you select for donuts? From a shop that only has three different kinds. So in other words, this is not a good shop because it only has three different types of donuts. Well, it depends, unless it has your favorite type. Okay. Yes, we're not doing section 6.4. You're correct. We are skipping section 6.4. Okay, so chocolate. If you really want to be picky about the chocolate donut, chocolate bar, maple bars, and guava filled. Yes, guava. Guava is one of my favorite ones. Okay. So, a couple questions before we do this. How many ways can you select 4 donuts from a shop that only has 3 different kinds? Okay. Now, the last sections that we have been doing counting with, even though I didn't really, well, I technically did say them, but I wasn't too explicit because we didn't have to be, but now I do. When we ordered stuff or permuted stuff, it was always an objects. No, let me repeat that. It was an distinct objects and distinct objects, such as, let's say I want to, or in how many ways can I put 4 people in a line? Well, that's a permutation, and each of these people are distinct. Each person is different from one another, assuming no twins or triplets or anything like that. Then it'll be 4 factorial, right? Something like that. Or if it was in how many ways can I select 3 cards out of 4 deck of cards, 4 deck of cards? We didn't care about the order either, so that was 4 choose 3 or 4C3. But they were still distinct because I said these cards were hearts, diamonds, spades, and clubs, but they were all distinct, meaning they were different. This section's about what if they're not distinct? What if repetitions are allowed? For example, how many ways can you select 4 donuts from a shop that only has 3 different kinds? So no matter how you look at this, you're going to select 4 donuts, right? There's going to be a donut that's gonna be repeated. It could be a chocolate, it could be a guava, it could be a maple bar. One of these donuts, it's gonna be repeated. You can't get 4 different donuts if you want. So this section's about doing combinations and permutations, but when dealing with repetition, they're not and distinct objects necessarily. Now we're dealing with repetition. That's essentially what this section is about. We're dealing now with repetition. Any questions on what I just said? No? Okay, I'm just trying to make sure. So repetition's allowed here, obviously. Does the order matter? Does the order how I select these donuts matter? Yes or no? No, right. The order doesn't matter. In the end, you're going to get a donut regardless. Well, not physically, but you know what I mean. Okay. The only thing that matters is the type of donuts. There's obviously 3 types here, 3 types of donuts. So, but it doesn't matter which one you pick first, which one you pick second, which one you pick third, blah, 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 and which one you pick fourth. I could just say first, second, third, and fourth, but it doesn't matter. Okay, so let's actually write this out. And I'm actually going to do it brute force. And what I mean by brute force, I'm going to do it the long way. And then I'm going to do it a different way. So let's say we pick these 4 donuts. Well, let's say that the first 4 donuts, I want them to be chocolate donuts. So I pick 4 chocolate donuts. So I'll call this for C for chocolate, maple bar M, and guava filled G. Okay, so there's no confusion. I'll make it, you know what, just so it could be more mathematically correct, I'll say C is equal to chocolate bar, M is equal to maple bar, and G is equal to guava filled. And these are all donuts. Donut. Copy. Paste. Paste. So let's say I select 4 chocolate donuts. Sweet. I selected 4. Repetitions are allowed. So we're good. I could have also chosen 3 chocolates and 1 maple. Or I could have chosen 3 chocolates and a guava. Or I could have chosen 2 chocolates and a maple and a guava. Or I could have chosen 2 chocolates and 2 guavas. Okay. Those are 5 possibilities so far. 1, 2, 3, 4, 5. Am I missing more? Obviously, I am, but those are the ones with the chocolates. Now let's start off ones with maple bars. Well, with maple bars, I could have selected all 4 of them to literally be maple bars. I could select 3 to be maple bars, and the last one could have been guava. Or I could have done 3 maple bars, and the last one would have been chocolate. Doesn't seem like I have that combination yet. Or I could have selected 2 maple bars, 1 guava, and 1 chocolate. Or I could have done 2 maple bars and 2 guavas. So far, so good. Any questions? Okay. Do I have another combination? Well, yeah. I could select it all four of them to be guavas. Or I could select the three to be guava and one maple. I could select it all three of them to be guava filled and one chocolate. I could select the two to be guava, one chocolate and one maple. Or I could select the two guavas. I don't know. Think, am I missing any? Oh, no, I don't. Am I missing any combinations? Two guavas and I can't do I can't do two chocolates because I already have that. Two guavas and two maples, I already have that. I feel like there's one more missing. Hmm. Chocolate maple. Oh, there is, you're right. So I'll just put it here. Chocolate maple. Completely missed that one. Thank you. Yeah, because I was gonna do guava again, but we already have those combinations here. So I can't do that. Okay. And I think that's it. I think that's all I have. Yeah, those are. Okay. So how many combinations do I have in total? 15, right? So therefore, there are 15 ways on how to do this. Or there's 15 ways to select four donuts. That's probably better. 15 ways to select four donuts. From three categories or three varieties. Because it was only three different types. So there's 15 ways. And you can always count them. 1, 2, 3, 4, 5. 1, 2, 3. 5 times 3, 15. Does everyone agree? Any questions on this? Any questions? Okay. Now, this is one way how to do it. Honestly, by brute force. It works. It works. It takes time. You have to write them all out, obviously, and then you literally count them. That's why sometimes this subject is just called counting, because that's literally what we're doing, counting. But there has to be is there another way how to do this? And the answer is yes. There is another way how to do this. And I'm going to show you, and I'm going to do it. I'm going to focus on this method by doing various examples of this. But yes, there is another way how to do this. So how do we do this? Well, let me rewrite the question. So I'm just going to copy it. And I'm going to need more space. So how else can we do this? Well, here's the thing. Imagine you're at the store, at this donut shop. Most likely the donut shops are all separated. And let's say they're not, but assume they are, okay? And it makes more sense. They're all separate because they're faster to get, they're faster to sell. You don't want to go like, oh, is this the guava fill? You don't want to guess, right? You don't want to like, oh, okay, I think this one's this one, so I'll put it in there. So in other words, you don't want all the donuts in the exact same place. You kind of want them separated. It makes them simpler to see, makes them easier to sell. So let's suppose you have a stand. Let's say I'm going to, and let's not go three-dimensional on it. Let's just keep it simple. Okay. And then we have the chocolate ones here. We have the maple bar here. And we have the guava one here. Okay. And then just to make it a little bit more visually appealing, let's say we have a couple of donuts here. So here's a donut, 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 donut. There you go. And also it's going to help with what I'm trying to explain here. Okay, so there are your donuts. Now the whole point is you're going to select from these options, right? That's what you can do. You're going to take one from here, take one from here, take one from here, and probably take one from here. When you already saw that when we wrote them all down, there's 15 different ways on how you could do this. But let's suppose you didn't know that. The idea is you can like, okay, I can select 4 from here. I can select 2 from here. Well, 4 from here, and that's it. Because the only thing you can select is just 4. So another way on how to figure this out is thinking of it in this manner. Let's forget. So let's assume that these donuts are in this container and they're all separated by these dividers. So let's make this picture a lot simpler. Let's just look at the dividers. Now, here are your dividers. These dividers separate the type of donuts: chocolate, maple, and guava filled. Okay, but now let's start saying you select ones. Well, one possibility is you could select 3 from the chocolate bars, and then you selected 1 from the guava filled. So this is how it looks like. You selected 4, you selected 3 from the chocolate bars, and you selected 1 from guava. But you selected none from the maple bars. Does this picture make sense so far? Okay, but now let's suppose you could have done this instead. You could have selected 4 guava. Then you have that type of picture. So what is this saying? Just in case you don't understand this. What this is saying is no chocolate bars were selected, no maple bars were selected, only the guava fills were selected. 4 of them. So that's that scenario. Or you could select 1 from the chocolate bar, 2 from the maple bar, and 1 from the guava bar, from the guava fill one. You could have had that picture as well. So this is saying select one from chocolate, you selected two from the maple, and you selected one from the guava. In the end, you still got 4 donuts. There's that possibility. Or there's a possibility of saying you selected all maple. So what is this picture saying? Chocolate bar, none. Maple, you selected nothing but maples. And guava fill, none. So here are 4 different examples of the same thing. Well, different choices, but they're still saying the same thing in terms of how many each one did you pick. Does everyone understand that so far? There's a reason why I'm doing this, and I'll get to that in a sec. But does everyone follow my pictures so far? Yes? Okay, I'm assuming. So why am I drawing these? Well, because another way how to think about this problem is what you're really doing is you have 6 objects. 1, 2, 3, 4, 5, 6. And all you're really doing is rearranging these objects. That's all you're doing, right? Because that's how I can look at this. It's just another way of how to rearrange this. Or I could have ordered it in this format. Or I could order this in this way. Or I could have came up with a different order. In the end, these are 6 objects that are being arranged in different ways. So another way of looking at it is in how many ways can you order two dividers and 4 asterisks. So another way of looking at this problem is I'm just moving around dividers and asterisks. How many combinations are there of that type? Do you see why I'm getting at now? Okay. But in the end, we're still selecting 4 donuts, right? We're still selecting 4 donuts. So by doing the problem like this, I kind of change the concept or how to view it differently. So what I'm really saying is the number of ways to select 4 donuts is the number of ways to select 4 positions of the asterisks from 6 positions. And since order doesn't matter, I'm going to state that it is the combination of having 2 dividers plus 4 asterisks, but I want to select 4 positions of those asterisks. I want to select the positions of the 4 asterisks, which is the same thing as saying C of 6 comma 4, which if you do the math, this is 6 factorial over 4 factorial, and then 6 minus 2 factorial. That is 6 times 5 times 4 factorial over 4 factorial. That's 4 factorial as well. Oops, not 6 minus 2, 6 minus 4. Sorry about that. So this is 2 factorial. Notice that 4's cancel out. I'm left with 6 times 5 over 2. That's just simply 15. Is that the same answer that we got earlier? Yes. And this is a different way of how to view this problem. So another way of thinking about it, like I said, is how many total positions do you have? And you're selecting this many asterisks with respect to the total number of positions. So the answer to this question will be the combinations of 6, 4, or 6 choose 4. Any questions on that? We'll do a couple more examples so you can see this a little clearer. We'll do a couple more examples, but any questions on this? Oh, can I zoom out? No? We're going to do a couple of examples of this, yes, because I can see how this could be a confusion at first. Now, another way you can look at it, and it's another way you can look at it, if you're like, oh, okay, can I look at it in terms of choosing where the dividers go? Like suppose I have 4 donuts here. Can I choose, oh, I want my divider here and I want my divider here, or I want my divider here. So in other words, selecting the positions of the dividers. Well, the answer is, yeah, you could view it as that way too. Why? Because 6, 4 is the same thing as saying 6, 2, C of 6, 2. So that's another way of looking at it. Amongst the 6 positions, I want to select 2 positions for my dividers. They're both going to be the same answer. Because if you do this work, notice that you're still going to get the same denominator here, which you're still going to get 15. So that's another way of viewing it. But we'll do a couple more examples if you want. Well, actually, I was going to do more examples either way. Okay, so let's try another one. Example. A croissant shop has plain croissants, cherry croissants, chocolate croissants. Literally, I'm making myself hungry with this. Bad idea to choose these examples. Almond croissants, apple croissants, and broccoli croissants. How many ways are there to choose? I'm going to do various examples with this thing so I don't have to keep writing it over and over. So let's do part A. A dozen croissants. Okay. So I'm gonna, to make it simpler, I'm probably gonna denote what each croissant represents, just so you can make it simpler. So a shop has plain croissants, so I'm gonna say PC for plain croissants. Cherry croissants, CHEC, that'll be cherry croissants. Chocolate croissants, CHO, and then C, chocolate croissants. Just in case I have to write these again. Almond croissants, so AL for almond croissants. Apple croissants, APC for apple. And lastly, broccoli croissants, I'll probably just use BC for broccoli croissants. Okay. I'm gonna give myself some space. And I'm gonna use this for all of them, just because every time I introduce a variable, I have to at least know what it's defined, what does it mean. I can't just introduce it and assume people know what it means. Okay, so plain croissants, cherry croissants, chocolate croissants, almond croissants, apple croissants, and broccoli croissants. Okay, sweet. So how many ways are there to choose a dozen croissants? Clearly, well, repetition is going to happen here. Order doesn't matter which one I pick first, which croissant I pick first. Does the order matter? Yes or no? No, right. The order doesn't matter. The order of croissants doesn't matter. I don't care if I pick the broccoli one first and then the apple one. It does not matter. Okay. So how do we do this? Well, one way is to brute force this, kind of like how we did with the donuts. But clearly, this is more options than the donuts. So doing the brute force one will be tedious and it's just going to take a long time. So let's think about it a different way. The other way is, notice that all of these are completely distinguishable. And what I mean by that, they're all different. They're all different. And in the end, you're going to select 12. So, because they're all different, that means another way I could picture this is that they all belong in their own specific place or their own specific box. So I can say, here are my plain croissants, here are my cherry croissants, here are my chocolate croissants, here are my almond croissants, here are my apple croissants, and here are my broccoli croissants, and that's it. And just to make sure, I should have six places, because I think I have six. 1, 2, 3, 4, 5, 6. Yeah, so 6 different locations. 1, 2, 3, 4, 5, 6. Perfect. So I can look at it in terms of asterisks and dividers again. I'm going to copy this just so I don't have to rewrite it. And I could say, okay, I'm going to select stuff. In here are nothing but plain croissants. Here, cherry croissants, chocolate, almond, apple, and broccoli croissants. They all have their specific locations. So I can say, okay, I'm going to pick a couple from the plain croissants. So I'm going to pick probably like 4. I'm going to pick broccoli croissants. So I'm going to select that, 1. I'm going to select, so that's 5, 4 of the apple. So that's 9, 2 chocolates, and another one of the plain. So that should be 12. So notice I didn't select any from the cherry or the almond. However, that's just one scenario. And I want to make sure I have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. That's only one scenario. Some of you would have picked nothing but cherries if that's your favorite croissant. Some of you would have picked nothing but broccoli ones. So all of these would have been empty. Some of you would have picked a combination of probably only these 4. Maybe 3, 3, 3, 3 to make 12. In other words, there's so many combinations. In the end, all it really comes down to is just a way of how to order all of this. Dividers and these asterisks. So how many total positions do you really have? How many positions are we really looking at? Well, how many croissants are we picking? Croissants. How many croissants are we selecting? 12, right, a dozen. How many dividers do we have now? Five. Right. So maybe I'll hope if I write it out like this so you guys can see it better. So so what we really have in total is actually 17 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 positions. So I have 17 positions. So that means I have 12 doesn't have to pick plus 5, comma, and the end, I want to select 12 croissants. So in the end, what I really have is out of 17 positions, I want to select 12 for my croissants. And whatever that answer is, that's the solution. Does that make sense? Because again, what it really comes down to is ordering these 17 items. Because that's what it is. It's a combination of all of these 17 items. How can I order this? How can I arrange these? But in the end, I know I'm selecting only 12 positions. Why only 12? Because I only want 12 croissants. But another way you could look at it if you want is out of 17 positions, I'm selecting 5 of those so I can put my dividers. So if I have just literally 12 croissants in line, where can I divide them? Where each one tells me this is plain, this is cherry, and this is so on and so on. And why can I say 17 choose 5? Because 17 minus 12 is 5. Both of these will be equal statements or equal values. Does that make sense? Of course, I'm going to do another one, a couple more, but does that make sense? Any questions? So I'm counting the asterisks and the vertical lines, pretty much. Yes, I'm counting those. That's really what it comes to, because I'm just organizing all of these. Because you could have said, oh, I chose this instead, and I chose one of these, and I chose one of these, and no broccolis. Knows that that's a different combination. But in the end, it's just a combination of ordering this around, arranging it in different ways. Exactly. So it's a dozen plus the dividers. Your book has a different formula. I just don't like it. You can use the book ones if you want, but this one just makes more sense in my head. But again, once you read the section and you look at that, and if you prefer the formula that they use, go for it. There's nothing wrong with it either. Now, let's look at another example. What if it was, just so you could get the gist of this, 4 dozen? Well, obviously, I'm not going to draw 4 dozen. I'm not going to have to draw all of this, but you get the general idea. Now we're rearranging 4 dozen. So now we want 4 dozen donuts, right? So in the end, I could have picked 12 here, 12 here, 12 here, 12 here. That's one possibility. I could have done 10 here, 2 here. That's 12. And then 4 dozen, that's 48. So I have 12. So I could have done 16 here. And that's 38. So I could have done 5 here and then 5 here. So there's, in other words, it's still a way of rearranging the dividers and the dozen donuts. So if I wanted to find a solution, I could just say, oh, wait, the solution is this then. It's a combination of, well, how many donuts are we selecting? Just how many donuts? First, the donuts. 48, right? Plus the dividers. How many dividers will we need? 5, exactly, because there's only 5 different, there's 6 types of donuts, and to separate them, you need 5 dividers. Comma, well, I'm selecting 48 donuts. So in the end, it's just simply C of 53, comma 48, whatever that is. Obviously, I didn't even bother to figure it out. I just like, oh, okay, yeah, that's it. I'm sure you guys know how to do that by now. Any questions? So do you see the pattern? The pattern pretty much is how many you're selecting plus the dividers, and that's it. The pattern for this here. Let's try another one. What if I would have said 3 dozen? What would this be? I'll give you like a minute. And then in a minute, I'll ask what the answer is. 3 dozen. So now you're picking 3 dozen donuts. So what will be this at the end? How many ways? And this tells me how many ways. Obviously, we have to do it, but I'm not going to bother doing the calculation. And again, this is a different way how to view it. If there's other ways on how to do it, but this is the technique that they're showing in this section. All right. I didn't give you about a minute, so I gave more like 50 seconds, but let's see if you guys got this. C of, well, 3 dozen, that's 36, plus 5. And in the end, I still want to choose 36 donuts. The 5 means the dividers. So I have 41, comma 36, and that will be it, whatever that solution is. Okay, let's try another example. Same thing, I'm still sticking with the croissants. 4 dozen with at least 2 of each kind. So 4 dozen with at least 2 of each kind. So that's interesting. We want 4 dozen with at least 2 of each kind. What does it mean by 2 of each kind? What does that mean? Two of each kind. Not 2 raised times 12. 2 raised to the 6, not quite. Not quite. But there's the right idea is there. It's not 2 to the 6. So what it means by 2 of each kind means this. So if I still have my dividers, that means I'm already selecting guaranteed 2 donuts for each kind, or 2 croissants of each one. So already guaranteed. I'm selecting 2 of each one. So that means that in my box or wherever I'm putting these, I already selected 2 of this, 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 and 2 of that. Well, there's only one way how to do that. There's only one way how to do that. There's only one way on how to select one plain donut. And there's only one way how to select another plain donut. So 1 times 1. There's only one way of selecting, I forgot what that represented, cherry donut, why do I donut? Cherry croissant, and there's only one single way to do a cherry croissant. Same thing with the next one. There's only one way how to pick a chocolate croissant and another one way how to pick a chocolate croissant. So you're guaranteeing that in wherever you're placing these croissants at, you're going to have 2 of each one. But you want 4 dozen, right? How many donuts do you have here only though? So how many donuts have already been selected? 12. But you want 4 dozen. So how many donuts are, why do I keep saying donuts? So how many croissants are left to choose? 36. That's correct. So now we have to choose 36 croissants. Well, ignoring the fact that we already have this picture here, I can place some croissants here. I can place some more croissants here and some more croissants there until they add up to 36. Or I could place all 36 croissants here because I want nothing but of this type. I want more of this than I do of the other ones. So it goes back to what we originally had. Now you have 36 things plus the dividers. So 36 plus the dividers, which are 5, and you're still selecting 36 locations for those croissants. So you have C of 41, comma 36. So when you have something of this form, at least 2 of each kind, that means you're already selecting 2. So you're already taking away from the total amount that you need to select at the end. Since the total amount is 4 dozen, that's 48 croissants that you need to select. But since you're already saying 2, or I'm going to select 2 of each kind, you're already guaranteeing, okay, I already have 2 of each kind. Now, what about the rest? Does that make sense? Any questions? Any questions? Yeah? Okay, sweet. Now, I'm going to do one more example, and then I'm going to give you a break so you can think about this example and see how you do with this one. A, B, C, D, E. And here it is. 4 dozen with at least 1 plain croissant, but no more than 3 broccoli croissants. So I'll pause the image here. We'll take a 5-minute break about, and then when I come back, I'll talk about this one. Okay, and we're back. Ugh. Let me reshare soon. Okay, so let's see if you guys got this. And this one's a little tougher. 4 dozen with at least one piece, one plain croissant, but no more than 3 broccoli croissants. Okay. So the thing here is you want to select at least one plain croissant. So that means you could have one or up to 48 croissants of plain croissants. All of them could be plain croissants because it says, but no more than 3 croissants, which means you can have 0 broccoli croissants, 1 broccoli croissant, 2 broccoli croissants, and 3 broccoli croissants. So those all those cases. So this becomes a little bit more complicated than what it seems, because you can have 1 croissant, 1 plain croissant, 2 plain croissants, 3, 4, 5, all the way to 48. And that seems like a lot of combinations that we're gonna have to do just for that. And the same thing with the broccolis. We have to take that to account. So this could take a while. But is there another way how to do this one? And there is. So how do we do this one? Now, what's another way of looking at it? Well, another way of looking at it is this. Let's just assume the first condition, at least 1 plain croissant. So let's just look at that. Suppose the only restriction right now is 1 plain croissant. So suppose the only restriction is at least 1 plain croissant. Let's just suppose. Well, in order to pick 1 plain croissant, there's only one way to do that, right? Because there's only one type of plain croissant. There's not a different type. So there's only one way to do that. So 1, sweet. Which means if there's only one way to how to do that, how many croissants are left that I'm going to have to order or select from, I should say? How many total croissants would I need to pick next? 47, exactly. So I need to pick 47 croissants. But again, if we're doing it in the process of asterisks and dividers, then I'm looking at 47 plus 5 dividers, or 52 positions. And amongst those 52 positions, I'm going to select 47. So my solution so far is just this, with that restriction alone. I haven't taken the other restriction yet to account. But does that make sense so far? Okay. But now let's also take the restriction of no more than 3 broccoli croissants. But I'm going to do it a little bit different. I'm going to say this. Instead of saying no more than 3 broccoli croissants, I'm going to say, suppose we have the restrictions at least 1 plain croissants and the restriction for, or I should say at least 4 broccoli croissants. And there's a reason why I'm saying that. Okay? Suppose we have the restrictions at least 1 plain croissants and at least 4 broccoli croissants. And you'll see, why 4? Why 4? We say no more than 3. Well, let's suppose we pick 4 more. So then to pick the plain croissant, there's only one way how to do that. We already know that. We already know how to do that. That's one way. But now we want 4 broccoli croissants. Well, there's only one way how to do that as well. Because I pick one broccoli croissant, there's only one way to do that. Pick another broccoli croissant, that's one way. Pick another one and pick another one. So these represent all my broccoli croissants. There's only one way how to pick a broccoli croissant. But that only gives me a total of 1, 2, 3, 4, 5 croissants that have already been selected. So how many more do I need to select? If I still want 4 dozen, because I do. 44. So another way I could view this is 44 croissants plus the dividers. So 44 plus 5. Actually, it wouldn't be 44, 43. 43 plus 5. Because there's already 5 croissants already selected. So 5 minus 48 is 43. And then we want 43 positions. So in the end, we have C of 48, comma, 43. Obviously, I'm not done because I'm going to do something with these both numbers. But does everyone understand these two things first? Any questions on these two things? How I got this and that? Just waiting to see if anyone has any questions on it. I'm not frozen. Okay, doesn't seem like it. Okay. Now, how did I get 43? Because 5 croissants have already been selected. At least one, oops, I didn't even write one. At least one plain croissant and at least 4 broccoli croissants. So 3 or more and 4 or more. So I'm going to say, okay, I'm going to pick at least one. So this set is going to contain at least 1 croissant, and it's going to contain at least 4 broccoli croissants. So in total, 5 croissants have already been selected. But since I still want 4 dozen, that means I need 43 more croissants that need to be selected. Does that clear it up for you now? Now, so why did I do 4 more when the restriction says no more than 3 broccoli croissants? Because one, it's a lot more difficult to figure all of this out the way it is. So the way I'm doing it is this. Assume we have a set of croissants where this set represents croissants that have at least 1 plain croissant, but this also has the possibilities of having broccoli croissants that have no broccoli croissants, 1 broccoli croissant, 2, 3, 4, 5, all the way to 48. So anything between 0, 48 broccoli croissants, this set can contain. And this set will contain all possibilities of having at least 1 plain croissant and at least 4 broccoli croissants. So 4 or more. So what I'm trying to get at is if I want to find what I was originally finding here, where I have at least 1 plain croissant, but no more than 3 broccoli croissants, all I have to take is the set that has all those possibilities and subtract it from the set that has the possibilities of having at least 1 plain croissant and at least 4 broccoli croissants. By subtracting those, I get what I want, which is going to be the set of 4 dozen that at least have 1 plain croissant, but no more than 3 broccoli croissants. Does that make sense of why I'm subtracting it now? And why I did it this way? So it's just a much quicker way if you want to look at it in that terms. Any questions? Why did I subtract 5? I'm not subtracting 5. Oh, 43. Because 5 have already been selected for this scenario here. 5 croissants have already been selected, at least 1 and at least 4. So 1 plain croissant and 4 broccoli croissants. So whatever set this is, whatever combinations these are, they must have at least this in them, which means 5 have already been selected. So you only have 43 left to choose of croissants because we want 4 dozen and 5 have already been selected. So you have 43. So why did we choose one more than 3? Because it says no more than 3. So I'm trying to do the opposite of what this means. So, okay, now you got it. Okay, sweet. And that's how you do that. Now, this method can also help with other types of questions, such as this one here. Why did I add 4? I didn't add 4. Did not add 4. Okay, so let's do another type. I don't know what you mean by add 4. I did not add 4. Oh, you're talking about this part. I see what you're saying. Why am I saying at least 4 BC? Because it says no more than 3 BC. So what I'm doing is I'm subtracting the possibilities of having more than 3. So 4 and more. Because if I take away those possibilities from all the possible ones of combinations, I'm going to get what I want. At least 1 plain croissant, but no more than 3 broccoli croissants. That's what I'm doing. Okay. Let's do another example. How many solutions does the equation x sub 1 plus x sub 2 plus x sub 3 is equal to 11 have where x sub 1, x sub 2, and x sub 3 are non-negative integers? Okay. So we're not interested in finding the exact solution. Doesn't say that. It just says how many solutions does the equation have? So how many solutions are possible when there are non-negative integers? Obviously, one way I could do this is literally do it by brute force, write all the possibilities. It could be done because it's a small number, but it could be done. It's going to take time, but I'm looking at an order triple, something of x comma y comma z, if you want to look at it that way. Okay. But there's another way how to look at it. And actually, it can be looked at as the same ways as how we've been doing the bagels and the donuts, or the croissants and the donuts, looking in that sense. It can be done similarly the exact same way. But how do we look at it? Well, this is how we can look at it. Let's look at what we're trying to make first. We're trying to make 11, right? Trying to make 11. So the way we could look at it is in this way. Suppose we have 11 ones. So let's see if I did 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's suppose I have 11 ones. Now, this is actually the same idea. I have 11 ones, but notice that they're being separated here. X sub 1, X sub 2, and X sub 3, meaning I have 3 categories or 3 boxes. So if I want to break this into 3 boxes, these ones into 3 boxes, how many dividers would I really need? 2, right? I could put a divider here, and I could put a divider here. And notice what this does. This tells me that this is X sub 1, this is X sub 2, and this is X sub 3. So X sub 1 represents the integer 2. X sub 2 represents the integer 1, 2, 3, 4, 5, 6. And X sub 3 represents the integer 3. And you know all of those are going to add up to 11 because you have 11 single ones. So the way you can look at this is, again, if I rewrite this, oops, not color, copy, or if I copy this, let me just copy, let me do this. Copy. I could have put the dividers here, right? Or I could have put the dividers here. Or I could have put the dividers here, right? Where this says X sub 1 is 1, X sub 2 is 1, X sub 3 is 9. Here this says X sub 1 is 1, 2, 3, 4, 5, 6, 7. X sub 2 is 2, X sub 3 is 2. Here states X sub 1 is 0, X sub 2 is 0, and X sub 3 is 11. And that is true, because 0 is a non-negative integer still. So all I'm doing is just organizing this again like the donuts and the croissants. So if I want to find a solution of this, all I really have to do is just say, okay, there's 11 ones, and there's 2 dividers, and in the end, I'm selecting 11 positions. Or if it helps, the same thing as saying C of 13, comma 11. Or the other way of looking at it is C of 13, comma 2, because 13 minus 11 is 2, and so these are equal. And if you want to view it in this manner, there are 13 positions, and you're going to select 2 positions in which the plus signs will belong between the ones. And whatever that answer is, that's the answer to this. So notice that this method can actually help with problems like this if you're just interested in finding how many solutions. Obviously we're not asking, it is not asking what the solutions are. It's just asking how many are there. And if you actually find all the solutions, which I'm sure you could do it, it's going to be 13 choose 11, which if I do it really quickly, I don't know what that number is off the top of my head, honestly. It's just faster if I just type it in. I was trying to, dang it. 78. So there's 78 choices. There's 78 solutions, I should say. 78. And if you actually write them all out, you will get 78. Any questions on this? Well, what if we have a restriction on it? What if we have this restriction? So the exact same question, but now we have a restriction on it. And here's my restriction. X sub 1 needs to be greater than or equal to 1. X sub 2 needs to be greater than or equal to 2. and x sub 3 needs to be greater than or equal to 3. Okay, so this is my restrictions. So let's actually do it. So x sub 1 needs to be greater than or equal to 1. X sub 2 needs to be greater than or equal to 2. And x sub 3 needs to be greater than or equal to 3. That's what they're saying here. Well, all they're saying is this, that x sub 1, another way of looking at it is x sub 1 needs to be a number that's bigger than 1. So I'm just going to say, okay, that's 1. X sub 2 is a number that's bigger than 2. So initially, it should start at 2. And then x sub 3 is a number that's larger than 3. So I'm going to start it at 3. Larger or equal to, sorry. Greater than or equal to. Okay. But this also tells me how many ones have already been selected for these x's. How many ones have already been selected in total? Six, right? So this actually goes back to the croissant idea of this one here. So 6 ones have already been selected because those belong in specific x variables. Because we want x's to be a specific number. We want this one to be bigger than 1 or equal to 1, this one greater than or equal to 2, and this one greater than or equal to 3. So all of these have already been selected, which are 6 ones. So that means in the end, they have to add up to 11. But already these 3 add up to 6. So since they already add up to 6, how many are left over that I need to care about selecting to belong in whichever one of these? How many are left over then? 5, right? So that means I'm going to take 5 plus my dividers, which is 2 of them, and I'm going to, so what I really have is 7 positions, and I'm going to choose 5. So this is going to be C of 7 comma 5, and that's the solution to this one. Any questions? No? Okay. Now, let's talk about another thing. Because all we done are repetitions with combinations. But what if we have something like this now? How many different strings can be made from the letters? And let's start with this taxi. So how many strings can I be made from the letters taxi? Well, does this have any repetitions? No, it doesn't have repetitions. So that means I have 4 choices. 1, 2, 3, 4, and I want to make a string. Okay, so it's going to be 4 times 3 times 2 times 1, which in the end, this is just simply 4 factorial, whatever answer that is. It's 24, obviously, but that's it. How many strings can be made from the letters taxi? 24 of them. because you can rearrange them in whatever way you want. And notice that it was just 4 times 3 times 2 times 1 because it's a string. What if the word was this one though? Falafel. Does this have any repetitions? Yes. And what are the repetitions? F, L, and A. Exactly. The F's are being repeated, the A's are being repeated, and the L's are being repeated. Now, since I'm creating a string out of these letters, does the order matter? Does the order matter? Does order matter here? Well, if you don't know, the order doesn't really matter here. Order doesn't matter. So order doesn't matter. So that's important. Order does not matter. Okay. Now we want to create different strings. So that means I'm going to move these letters around. How many positions do I really have? Well, I have 1, 2, 3, 4, 5, 6, 7 positions. So I have 7 positions. Okay, so let's organize these. So we have 7 positions. So let's talk about the F's first. We have 7 positions, but we have only 2 F's that we have to organize. So I'm going to say 7 choose 2. I'll write it like this. 7 choose 2. Sweet. Then we have the A's to worry about. Times, well, we chose 2 positions for the F's, which means how many positions are left for the A's? Do I still have 7 positions or do I have less? I have 5. So 5 positions left for the A's and there's only 2 A's. Then let's do the L's times the L's. We'll have 2 L's, right? Okay, so I'm going to do, how many positions do I have left now for the L's? Is it still 5 or is it 3? Or is it back at 7? 3. So 3 choose 2. So now I choose the position for the L's. And then lastly, the E's. Well, I have 1 position left, but there's only 1 E left. Yes, you could have, if order doesn't matter, you could have done 7 choose 1 if you would have started with E's. That is correct. There's nothing wrong with that. As long as you keep making sure that it minimizes. Now, we're actually going to do this one. I'm going to write it out, and you'll see why in a second. Why I actually want to do this one. This is the same thing as saying 7 factorial over 2 factorial times 5 factorial. Times the next one is 5 factorial over 2 factorial times 3 factorial. Times 3 factorial over 2 factorial times 1 factorial. And lastly, the last one, 1 factorial over 1 factorial, and then 0 factorial in the denominator, like that. So that's what we have. But let's actually multiply these out. I'm going to get 7 factorial times 5 factorial times 3 factorial times 1 factorial in the numerator. And then on the denominator, I'm going to get 2 factorial times 5 factorial times 2 factorial times 3 factorial times 2 factorial times 1 factorial times 1 factorial times 0 factorial. Okay. Now, what happens here? Well, if you notice, what cancels already out? These 5 factorials, the 3 factorial, and this 1 factorial cancel out. So in the end, we're simply just going to get 7 factorial over 2 factorial, 2 factorial, 2 factorial, and 1 factorial. The 0 factorial I'm going to ignore because 0 factorial is just 1. And this is all for the word falafel. But this is why why I actually wrote this one out, like I did the factorials and simplified it. Because if you notice, this actually has a specific, this is saying something that you can relate to the word falafel. Falafel is 7 letters. So on the numerator is 7 factorial. The denominators, 2, 2, 2, and 1, represents the number of repetitions of each of the letters. F repeated twice. A repeated twice. L repeated twice. And 1 repeated, E repeated once. So another way how to figure this out without having to do all of this is just simply doing this. And it will work for any letters if you're doing this method. Or if it's asking you how many different strings can there be for the word, for the letters of falafel. How many strings can be made from the letters of falafel? So I could give you another example, such as this one. Bookkeeper. And I ask the same question. How many strings can be made from the letters B-O-O-K-K-E-E-P-E-R, bookkeeper? Well, the first thing I want to do is just count how many positions I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 positions. So it's going to be a fraction on the numerator is 10 factorial. On the denominator, my more important things are anything that repeats. Do any letters repeat here? If so, which ones and how many? E's, K's, and O's repeat, right? So let's look at the O's. The O's repeat twice. So I'm going to divide it by 2 factorial. The K's repeat twice as well, so 2 factorial. The E's repeat 3 times, so 3 factorial. I don't have to worry about the ones because 1 factorial is not going to affect it at all because it's just 1 times 1. So it's not going to affect it. So I don't care about the ones, nor do I need to write the ones. But this is the solution. Whatever that is the solution. Any questions? Okay, let's try another one. Obviously, we're only going to do this section today. We're not going to just start chapter 7. Distinguishable objects and distinguishable boxes, meaning you can tell the difference. And I even misspelled that. So distinguishable, if you don't know what that means they are different. You can clearly tell the difference. So example. Or now we're looking at it unique. No, not unique, distinct. So how many ways are there to distribute 15 distinguishable objects into 5 distinguishable boxes so that the boxes have 1, 2, 3, 4, and 5 objects in them, respectively. So in other words, you have 5 boxes. So how many ways are there to distribute 15 distinguishable objects into 5 distinguishable boxes so that the boxes have 1, 2, 3, 4, and 5 objects in them, respectively? So what they're saying is, if you have 5 boxes, the first box has 1, the second box has 2, the third box has 3, the fourth box has 4, and the fifth box has 5. That's what they're saying here. Okay. So let's try and work this one out. So this is an example where you have distinguishable objects and distinguishable boxes. Okay. So you have 15 distinguishable objects into 5 distinguishable boxes. So let's go with the first box. There's 15 objects, but one of them has to go, at least one of those objects has to belong in that box. So I'm going to say that 15, comma 1, and it's going to be choose. So it's going to be a combination. So there's my first box. The second box is going to have 2 items, but one item was already put in one box. So that means I should have 14 combination 2. My third box should have 3. So combination 12, comma 3. And then the fourth one should have 4. So 9, comma 4. And the last one should have 5. So I have 5, comma 5, because that's how much I have left over. Any questions on this? Now, if we simplify this same thing as saying 15 over 14 times 15 factorial. Then 14, comma 2 is 14 factorial. Denominator's 2 factorial times 12 factorial. Actually, this should be 15. This should be a 1. That should be a 14. I messed it up there. Okay. 12, comma 3, 12 factorial on the numerator. And then denominator, 3 factorial times 9 factorial. Then on the numerator for 9, comma 4, 9 factorial. This will be 4 factorial, 5 factorial. And the last one, 5 factorial on the numerator, 5 factorial, and 0 factorial. But if you look closely, notice that the 14s cancel out. So these will cancel out. Notice that the 12s cancel out, the 9s cancel out, and the 5s cancel out. So if I had to rewrite this, this is just 15 factorial over 2 factorial, 1 factorial, 3 factorial, 4 factorial, 5 factorial. And we can ignore the 0 factorial since we know that's just simply 1. But this is the same thing as the one with the letters. Since all of these are distinguishable and we have distinguishable boxes, I could have just said 15 factorial divided by the number that each box contained. So the first one contained 1, the second 2, 3, 4, and 5. So another way you could think about this is you have 15 letters, and some of them are repeats. That's another way you could look at it. But I don't know if I want to say letters because they say it's distinguishable, so they're all different. So maybe not, that's not a good analogy. But when you have distinguishable boxes and distinguishable objects, it's just simply this rule. N factorial divided by whatever these you have in each one of those boxes. Just name each object a letter. Yeah, you see what I'm saying? You run into that problem. Like, I know what you're trying to say, because that's literally what I was trying to say. But we run into that scenario because they have to be distinguishable. There is, and here is that theorem. I'm going to write out that theorem for you guys, the one I was trying to talk about. Theorem 6.5.4, the number of ways to distribute, because that's what we're doing with distributing, and distinguishable objects into K distinguishable boxes, so that N sub I objects are placed into box I, where I is equal to 1, 2, 3, all the way to K, equals N factorial over N sub 1 factorial, N sub 2 factorial, all the way to N sub K factorial. So it's pretty much what we were doing earlier. So since I'm distributing 15 distinguishable objects into 5 distinguishable boxes, and each box contains a specific amount, all I really have to do is just this equation, and that's it. Any questions on that? So similar to the letter one, but it's not the same because you're literally distributing stuff here. That's what you're doing. Oh, I think I know how to the analogy. Like a recycle bin, but assuming it's a very specific recycle bin. Like all the bottles can be distinguishable because you can have different types of bottles, but they can make differently. Like some are glass, some are metal, some are aluminum, some are ceramic, and stuff like that. And you can think of your bins as a ceramic recycling bin, a metal recycling bin, a glass recycling bin. Yeah, that will work. Yeah, they're all distinguishable, but some of them still belong in this specific type of box. Okay. What do you have indistinguishable? Objects. And distinguishable boxes. So undistinguishable objects are things that are not different. They're identical. They're identical. Distinguishable things are, they are different. So here's an example of that. How many ways can you distribute how many ways, can you write it correctly? How many ways are there to distribute, that doesn't look like a bar, $12 indistinguishable balls into 6 distinguishable bins. How many ways are there to distribute 12 indistinguishable balls into 6 distinguishable bins? So what if we have something like this? We have indistinguishable objects, meaning I can't tell them apart. These objects are identical. And then I have distinguishable boxes, which I can't tell the boxes apart. Well, this is actually this example here, or this scenario here, is actually very similar to what we have done before. Think of the scenario of what we did with the croissants and the donuts. Yes, they were different types of donuts, but they were indistinguishable in terms of the chocolate donuts, the chocolate bar donuts. One chocolate bar donut is the same as the other, and as the other, and as the other. Same thing if it was an apple croissant. This apple croissant is the same as this one, as the next one, as the next one, assuming none of them are specially made or anything like that. So this is the same scenario. So another way you could think about this is you have 6 bins, 6 distinguishable bins. So they're all different. So I can line them up and use dividers. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This represents bin 1. This represents bin 2. This represents bin 3. This represents bin 4. This represents bin 5. And this represents bin 6. But in the end, you're placing 12 indistinguishable balls into these bins. So I could have 6 balls in a first bin. Is that 6? 1, 2, 3, 4, 5, 6. I could have 2 in bin 3. I could have, that's 8. So I could have 1 in bin 6, 9. 2 in bin 2, 10. And 1 in bin 5, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's how I can look at it this way. The balls are indistinguishable, but the bins are distinguishable. I can tell them apart, the bins, but I can't with the balls. Same thing with donuts. I can't tell these donuts apart, but I know where they belong in. So this is the same scenario, so that means I'm going to do it the same way. It's combination, since order doesn't really matter, of I have 12 objects plus the number of dividers, which is 1, 2, 3, 4, 5, comma, choose 12 locations. So this is C of 17, comma, 12. And that pretty much ends this section. There are other scenarios of other like cases, but that's why I have you guys read the book as well. And also I'm running out of time too. So we're pretty much done with chapter 6. Make sure you read this section. Next week we start with chapter 7. But other than that, I'll see you guys next week. Be safe. Make sure you be extremely safe this weekend. Other than that, if you have questions, let me know.